Now microphone is on. No? What? Okay. Now we are going to start with Lagrange's mean value theorem. So in Lagrange's mean value theorem, what is that? Later on we can switch to Rolle's theorem, that is subcase of this. So first we start with the Lagrange's mean value theorem, that is LMVT. Same only, nothing is there. So if we have fx continuous in the closed interval a to b and fx is differentiable in the open interval a to b, and then there exists at least one chotu c belongs to a to b such that f dash c equal to f of b minus f of a, down we have b minus a. So this is LMVT, and Rolle's theorem is a special case of LMVT. So in Rolle's theorem, first condition fx continuous in closed interval a to b. Second condition fx differentiable in open interval a to b. F at b equal to f at a. This is the third condition for Rolle's theorem. This implies f dash c equal to 0. Same thing, just in LMVT, f of b minus f of a we are writing, and in Rolle's theorem we are writing f of b equal to f of a. So they are not equal in this case. In case of LMVT. So Rolle's theorem is a subcase of LMVT. So for LMVT, if we draw that function, let's say like this, not like this. Why this Kolaveri? Very bad, but okay. So let's say this is some function. This point is a comma f of a. This is some point b comma f of b. So this chord slope is what? Slope of this chord f of b minus f of a down b minus a. So there at least one tangent which is parallel to this. So this point is c comma f of c, for which f dash c will be same as slope of the chord. So that is why we are getting f dash c equal to f of b minus f of a, down we have b minus a. Getting it? So in case of Rolle's theorem, what we have? We just had that functional value at a should be equal to functional value at b. So suppose if we take one function gx equal to, what we have, f of x minus f of a plus f of b minus f of a, down we have b minus a into x minus a. This is some function. Let's say this is function where fx is given continuous and differentiable in a to b, like this it is given. Now g at a is what? G at a is what? fa gone, a we put gone. So g of a is 0, g of b is 0. So if g of a is 0 and g of b is 0, g of a is 0 and g of b is 0, so gx is continuous G is differentiable and G of A is equal to G of B, both equal to 0. G of B also 0 na. G of B in this case B minus A gone, put na f of B, we have to put minus, this should be minus. So G of B also 0 we are getting. So now we can apply here Rolle's theorem. Yes or no? So now Rolle's theorem is applicable. On Gx. Rolle's theorem, what is the statement? Statement is fx is continuous in A to B, fx is differentiable in open interval A to B, f of B equal to f of A, then f dash C equal to 0. So here G dash C equal to 0. What is G dash C? Here. So using Rolle's theorem we can say there exists at least one C belongs to A to B for which G dash C equal to 0. So G dash X, what we are getting? G dash X. F dash X minus f of B minus f of A, down we have B minus A. So this should be 0. So what we are getting? F dash C equal to f of B minus f of A, down we have B minus A. So though we have that Lagrange's theorem is that Rolle's theorem is a special case of Lagrange's theorem, but we are using Rolle's theorem to prove Lagrange's. See, by defining this function, this is this let getting it? Yes or no? So let's say we have fx equal to x square plus x and x is given in 1 to 2. So find C of LMVT. So this function is continuous in the 1 to 2, differentiable also in open 1 to 2. So f dash C should be equal to f at 2 minus f at 1, down we have 2 minus 1. So f dash C is what? So LMVT is applicable. First fx is continuous, correct. Second fx is differentiable, correct. Third f at third is not needed here. If it is 0, if they are equal, it will come f dash C 0, and if they are not equal, then something will come. So we can apply LMVT. So if we can apply LMVT, what we are getting? This implies there exists at least one C belongs to 1 to 2 such that f dash C equal to f at B, that is f at 2 minus f at 1, down we have 2 minus 1. F at 2 is what? F at 2 is 6 minus 2 by 1, that is 4. F dash C is what? 2C plus 1, so 2C equal to 3. So C equal to 3 by 2. So that is yes or no? Okay. So let's say we have f is a thrice differentiable function. So 3 times we can differentiate that function. Thrice differentiable function with f at 1 1, f at 2 4, f at 3 9. Very difficult to judge that function. Yes or no? F at 1 is 1, f at 2 is 4, f at 3 is 9. Almost impossible. Huh? So first statement is, then there exists at least one C belongs to 1 to 3 such that f dash C equal to 3. True or false? One, two, three. What we can say? Fx is what we have? 2x 9 minus 1 8 by 8 1. Huh? F of 2 minus f of 1 in 1 to 3. So 1 to 2 if we apply, what we are getting? F of x is x square. So f dash x is what? 2c equal to f of 2 minus f of 1. Down we have 2 minus 1. So 2c equal to what we are getting? 4 minus 1. So that is 3. So c value what we are getting? 3 by 2. So we are getting 1.5. So 1.5 in 1, 2, 3. Correct only, no issue. There at least one C belongs to 1 to 3 where f dash C equal to 4. Such that f dash C equal to 4. So f dash C equal to 4, what we can write? F of 3 minus f of 1. So we are getting 9 minus 1 8 by 2, so 4. So 2c equal to f of 3 minus f of 1. Down we have 3 minus 1. So 9 minus 1 8 by 2 4. So we are getting c value 2. So at c value 2 we are getting in 1 2 3. So there exists at least one C belongs to 1 to 3 for which f dash C equal to 5. Three 2. 9 minus 4 5. Down we have 3 minus 2. Yes or no? So this is correct. Third, there exists at least one C belongs to 1 to 3 for which f dash C equal to 5. That is also correct. Yes or no? This we can write 2C equal to f of 3 minus f of 2. Down we have 3 minus 2. 9 minus 5. 9 minus 4. 5. So C equal to 5 by 2. C equal to 5 by 2 is 2.5 in 1 to 3. There exists at least one C belongs to 1 to 3 where f of C equal to 6. F dash C equal to 6. True or false? This is false. Not possible. Now, there exists at least 2C belongs to, try this, there exists at least 2C belongs to 1 to 3 such that f dash C equal to 2C. Yes, f dash C equal to 2C. What should we do? Let's say gx equal to fx minus x square. Now g at 1 is what? Say g at 1 is what? 0. G at 2 is what? 0. G at 3 is what? 0. This is differentiable function. Continuous also. So, from Rolle's theorem we can say that there exists at least one C1 belongs to 1 to 2 for which G dash C1 is 0. That implies G dash C1 is 0. What is G dash X? G dash X 0 means f dash X minus 2x equal to 0. This implies f dash C1 equal to 2C1, where C1 belongs to 1 to 2. Where C1 belongs to 1 to 2. In the same way we can say, so this we are applying in 1 to 2 we are applying Rolle's theorem. Now we can apply the same Rolle's theorem in 2 to 3. So we can say there at least one C2 belongs to 2 to 3 for which G dash C2 should be 0. So what we are getting? F dash C2 equal to 2C2. So combinedly what we can say? So from this alpha and beta, we can say that f dash C equal to 2C for at least 2 C1 comma C2 belongs to 1 to 3. Because this C2 is belonging from 2 to 3, that C1 is belonging from 1 to 2. Yes or no? Now write next, there exists at least one C belongs to 1 to 3 for which f double dash C equal to 2. Next is, there exists at least one C belongs to 1 to 3 such that f double dash C equal to 2. So what should we do for that? See from here, from these two we can say that G dash C1 and G dash C2, from these two. Which color? Oh, color depreciation. Delete. Green. From this and this, from G1 and G2, green 1 and green 2, what we can say? G dash C1 equal to 0 and G dash C2 equal to 0. So C1 belongs to 1 to 2. C2 belongs to 2 to 3. So let's say this is function. So this function is 0 at two values. So its differentiation will have one root. Yes or no? So Rolle's theorem on this. Now consider this as function. Rolle's theorem gives the idea about roots of its derivative. So if this is 0, this implies that derivative of this, so g double dash at c will be 0 for some c belongs to 1 to 3. So this is true. So g double dash c is what? G double dash x. G double dash x we can write, say, f double dash x minus 2. So g double dash c equal to 0 implies f double dash c equal to 2. Yes or no? So this way we can say. And there exists at least one c belongs to 1 to 3 for which f dash c equal to 3c. True or false? False. By contradiction we can say we are getting 2c. F dash c equal to 2c, not 3c. So this we can say. Now write next is Cauchy mean value theorem. Cauchy's mean value theorem. What is that theorem is? F and G are continuous on A to B. Two functions are there. F and G are differentiable on A to B open. Third, g dash x is non-zero for any x belongs to A to B. Let's say at any x belongs to A to B open. Then there exists at least one छोटू c belongs to A to B such that f of b minus f of a down g of b minus g of a equal to f dash c by g dash c, where obviously g at a is not equal to g at b. Now to prove LMVT, what we used, one function we used na. Now I got that same way we should use one function here. What should we write? Hmm? Let's say hx equal to f of x minus f of a minus f of b minus f of a. Down we have g of b minus g of a into, what should we write? G of x minus g of a. Proof we can say. So h at a is what? So this function we are let's say this function is like this. So h at a is what? 0. H at b is what? H at b is 0. So there exists at least one c belongs to a to b such that what we have? H dash c equal to 0. This implies f dash c minus f at a minus f at a will be 0, no? F dash c minus f of a will become 0, and this thing is constant into g dash c. Yes or no? So f dash c, f of b minus f of a, down we have g of b minus g of a into g dash x. So g dash c equal to 0. So what we are getting? We are getting same thing. F dash c by g dash c equal to f of b minus f of a. Down we have g of b minus g of a. Hence this is proved. So Cauchy mean value theorem is that if we have two functions which are continuous and differentiable and g dash x is non-zero in a to b, so we can write f dash c by g dash c equal to f of a minus f of a, f of b minus f of a. Down we have g of b minus g of a. So now consider one function consider that function f of x equal to x into sine of pi x, where x is greater than 0, and 0 where x is 0. Then the number of points in 0 to 1 where f dash x equal to 0, that we have to find. Everything is on record. What is coming? What? What is coming? 1. In 0 to 1, 1. Oh, it's very hard. How 1? So, in this f of 0 is 0, f at 1 is 0. Aila. So f at 0 is 0 and f at 1 is also 0. So in between 0 to 1, that f dash x they are saying. Huh? There are infinite intervals. There are infinite intervals for which function have same value, that is 0. So if there are infinite intervals, so there are infinite points in between its derivative will be 0. Because if we write sine of pi x equal to 0, what we are getting? Sine of pi x equal to 0, we are getting pi by x equal to k pi. So x equal to what we are getting? 1 by k. So in between 0 to 1, there are infinite intervals. At 1 by 2, 1 by 3, 1 by 4, 1 by 5. So there are infinite intervals for which function is continuous, for which function is differentiable. So its derivative will be 0 in between at least once. So if there are infinite intervals, in each interval 1, at least 1. So at least infinite we should say. Infinite. You are getting it or not? Not getting. This we can write f of x equal to 0. This implies sine of pi x equal to 0. Pi by x equal to k pi. Pi gone. X equal to 1 by k. K value 1, 2, 3, 4 like this. F of 0 what we are getting? F of 0 is 0. F of 1 by k is also 0. So Rolle's theorem is applicable if we are putting 1 by 2, 1 by 2, 1 by 3, 1 by 2, 1 by 3, 1 by 2 is it right? Or we can directly write this, na? 1 by 3, 1 by 2, 1 by 4, 1 by 3. Yes or no? Like 1 by k plus 1 to 1 by k. So there are infinite intervals. Hence there exists some c. There exists some c belongs to each interval such that f dash c will be 0. So we can say f dash x equal to 0 has infinite roots. F dash x equal to 0 has infinite points where c belongs to 0 to 1. Getting it? Yes, no, yes. So how many we are getting? Tell. How many? Infinite. Infinite 1 by 0. 1 by 0 plus. Getting it? Now let's say if alpha greater than 0, beta greater than alpha less than pi by 2, and if tan beta by tan alpha is greater than k, then k is what? What should we do? Solve. What one? Solve. What one? Fx is what we can say here. Fx, let's say fx is x tan x. F dash x is what? Tan x plus x secant square x. This is always positive. So f of beta minus f of alpha, down we have beta minus alpha. Equal to f dash c. F dash c is greater than 0. So what we got? F of beta is greater than f of alpha. So b times tan of beta is greater than alpha times tan of alpha. So tan of beta by tan of alpha is greater than alpha by beta. Huh? Huh? Which one? By taking function. They gave option in terms of alpha beta, so we have to choose that function. Actually, options are there in terms of alpha beta. Oh, when? Now only? You didn't say?